Hello everyone, I am Mohammad Amirul from University Tenaga Nasional. Today I'm presenting my final class project for digital logic class design. This project was given from my lecturer, Sir Dickson. So the project needs me to create a counter that display my student ID. So I want to demonstrate first. So my student ID is 0, 1, 0, 7, 3, 3, 6, and then it repeats again from 0. So that's my student ID. So I'm going to show you how I create this circuit. This circuit consists of 4 T flip-flops and a clock. This is a synchronous circuit because all the flip-flops are connected to one clock and it will change simultaneously. So let's get started. Firstly, we need to know the number sequence that we need. So in my case, my student ID is 0, 1, 0, 7, 3, 3, 6. So this is my number sequence, and then we need to know what type of flip-flop that we want to use. I would like to prefer to use a T flip-flop because it has only one input, and then the truth table of the T flip-flop there isn't a don't care condition. The don't care condition sometimes make things harder, so I want a consistent output or input. So type of flip-flop, I want to use T flip-flop, and then we need to know the number of flip-flop that we want to use. So there are two things that determine the number of flip-flop that we're going to use, which is the highest number and then the repetition of the same number. So in my case, the highest number is number 7. So high is number 7, and then number 7 in binary form is 111. So that is a 3-bit binary number. So we will use 3 flip-flops, one for each bit, and then the repetition of the same number. So what I mean by the repetition of the same number, so this is the highest. We need to know what is the highest. So the repetition here is 0, 1, 0. So zeros are repeated twice, and then 7, 3, 3. 3, 3 is repeated twice. So the repetition of the same number is basically 2 times, but we just need one extra flip flop. Why we need one extra flip flop? Because we want to the extra flip flop will be known as identifiers. It will tell the number apart. For example, 0, 1, 0. If without the extra flip flop, it will be look like this: 0, 1, 0. So the circuit cannot tell apart between this number and this number. So the repetition, so the one extra flip flop will give another input to tell them to tell the circuit that this number and this number are different, but the values are the same. Something like that. Imagine like you have two identical twins. You cannot tell them apart by their faces. The way that you tell them apart by maybe how they look, maybe how they're wearing their clothes, maybe their attitude, something like that. For another example is let's say 733. So 7 is 111, 3 is 011, and then another 3 is 011. So for the number 7 is not repeating, therefore we just put another 0. For the non-repeating number, we just put the a number 0, and then for the first tree we just put 0, and then for the second tree we just put 1. So total that four flip-flops will be used. And then after we know the sequence, we must create a state table. So this is my truth table for the T flip-flop. It will be used later on. So the state table. So this is the current number. So let's say this is 0, 0, 0, 0. This is 1, 0, 0, 0. That is 1, 0, 0, 0. 7 is 0, 1, 1, 1. 3 is 0, 0, 1, 1. And then the second tree is 1, 0, 1, 1. And then lastly we have 6, 6, 0, 1, 1, 0. So the next for the next table, we just put the next number over here. Let's say after 0 is 1, so we just put 1, 0, 0, 0, 1. So after the number 1 is 0, the second 0, so we just insert the second 0 here. And then the after second 0 is 7, so we put 7 here. And then after 7 we put the number 3, the first 3. And then after the first 3 we put the second 3. And then after the second 3 we put number 6. And then after number 6 it will repeat again back to 0. So we put back 0. So after you know the state table, we need to know the input for the T. So the way we know the input of the T is by comparing the QD and the QD plus 1. For this example, I will only solve for QD. For TD, my bad. So this is the table TD. So let's compare it together. So for the first 0 is the QD is 0, QD plus 1 is 0. So 0 and 0, the input will be 0. So the number 1, 0 and 1, 0, 1, the input will be 1. For the second 0, 1, 0. So 1 and 0, 1 and 0, the input will be 1. For the number 7, 0, 0 and 0, the input will be 0. Number 3, 0 and 1, the input will be 1. And then the second tree is 1, 0. For number 1 and 0, the input will be 1. And lastly 6, 0 and 0, the input will be 0. So from this TD, the input, we need to create a K-map that correlates with this equation. So we want to know TD equals to QD, and what is the relationship between TD and QD, QC, QB and QA. So to know that, we will use a truth table. So I create a reference truth table. This is my location for the first 0, 1, the second 0, and then 7, the first 3, the second 3, and then 6. So let's insert them. The first 0 is 0. If let's say the numbers like 0, 1, 0, 0 isn't in this table, so you just put don't care. 0, 0, 1, 1. That is number 1. So number 1 is 1. Second 0 is I think it was like 1. And then the 7 is 0. And then the first 3 is 1. And then the second 3 is 1. And then the third, and then the number 6 is 0. So from here you need to group them together to know the equation. So this is a don't care situation, so don't care can be either 1 or 0. So let's assume this don't care is 1. So we have a group of 8. 1 will become a group. And then we want to group these together. So we will use the overlap situation. One here, and then another one here. As you can see, so our equation is TD equals to QD, because this the first group, the group of 8, uh, this is not consistent. QD and QC, we just differentiate them, which one is more consistent. So QD is 1 and 1, but QC is 1 and 0. So QD is more consistent than QC, so QD is the equation. For the second group, the group of 4, the 0 and 1 and 1 1, 1 is consistent, so A is consistent. For QD and QC, 0 0 and 0 1, 0 is consistent, and 0 is different than 1, so QC should be Q bar. So that is all for today. Thank you for watching and have a nice day.